So we left off last time. We looked at what's called the limit of detectability, and that is ultimately the ultimately our flaws that we're going to find in infrared or thermography tend to have to be wider than they are deep, right? They tend to be more wide area flaws as opposed to things like cracks, which are very narrow but deep. Because I showed how the heat energy transfers through the part. A narrow, deep crack doesn't really block the transfer of energy, whereas a wide flaw will block the transfer of energy. It'll cause that contrast in thermal properties as I get there, and it'll change the diffusivity. It changes how the heat energy diffuses in the part. One of the things we can do to a limited extent is measure if we're doing raw image analysis. So we're just directly viewing our image. We can kind of get a general idea of the size, but oftentimes the apparent size and the true size are not going to be the same. Thermography is not a great method for doing measurement of area or measurement of length. You can get a rough estimate, but you're not going to get anything precise. You're definitely not getting anything to even the tenth or the thousandth of an inch, hundredth or thousandth of an inch. You might be able to get it within maybe an inch, half an inch, depending on the size, how close your camera is, and when you're viewing it during the excitation process. So typically indications are going to show up larger than what they actually are. And that's because you get that, because of diffusion of energy, you don't get a hard line, at the edges. You kind of get a gradient of temperature change. And so in order to increase that, we often use pixel processing. And there's algorithms that can look at that diffusion of energy and kind of figure out where is it due to a difference in the diffusivity of the material, and where is it due to the residual energy diffusing through the non-damaged portion of the material. And so other things is the accuracy as the lateral dimension approaches the detection limit. So as a flaw gets smaller and deeper, it reduces our accuracy. So accuracy is best for larger flaws or larger areas of damage. The other thing that we have is we can do our detection, right? We can take our pictures with our camera at various times during the excitation process, right? So for example, if your excitation process is it's oftentimes easier to do a cooling process than a heating. So if you put a part into an oven until it gets fully heat soaked, and then you take it out of the oven and begin to image it as it cools down, you tend to get the best contrast early when you do that. So as soon as you bring it out. But the contrast may not be significant enough. When you've put a part in an oven, for instance, the entire thing is going to get up to the temperature of the oven, say 200 degrees. And so initially you won't see a good area and a bad area, or a good area and a flawed area. But over time, you'll start to see those differences in diffusivity. But for time, you're going to get more of that kind of fuzzy diffusion around the edges of an indication. And so it's a balance between, do you have enough contrast? Is there enough temperature contrast between different areas of the part when you first take the part out of the oven or first start heating the part? Versus, how precise or how sharp of an image do you need compared to that more diffuse image you're going to get later on. Another way you can do that would be like if you have an aircraft in a hangar. If it's summertime and you're in the hangar is cooler than the outside, you can open the doors, right? The whole airplane's at room temperature. And if it's a hot day, you open the doors, it starts to warm up. You can image as it heats up. That's a passive form of excitation. Or winter time, you have a plane in a heated hangar, it's room temperature, and then you shut the heaters off, open the doors, now the plane starts to cool down, and you can image it as it changes. So we have to do our imaging as the temperature of the object's changing. You'll get that definition, the best definition or contrast will occur initially or early on. But at first, you won't see anything. When you very first open those hangar doors, everything in the airplane is the same temperature if it's been sitting there, say, overnight or for hours and hours. And so you won't see any kind of a difference until that energy starts to move through the part, starts to leave the aircraft, and then some more is left behind in certain areas and less. Right? Areas of skin, of bare skin, just skin, will cool off faster than areas where skin has like ribs and stringers behind it, right? Because there's more mass and material there that hangs on to that heat energy. So if it's cooling. So where you see it is something like this. So again, I mentioned the direct viewing above. This is an image of a flap. Often, a composite flap, often used to find what's called water ingress or moisture that's gotten into the composite layers, and that's what's being shown here. Compared to a pixel processing image below where we really can't see. Just looking at that, you and I probably don't see anything in that lower image. But if you apply some kind of a computer algorithm that's been designed to detect a certain type of flaw or discontinuity, it would be able to pick up those differences. It's looking, in that case, again, these are temperatures. Each pixel on there is a temperature that we've just overlaid colors on. But a computer wouldn't be looking at the colors, it's looking at the actual temperature measurements. So just some examples of excitation techniques. So passive, I mentioned, solar and ambient. I just talked about how each of those work, and they're good for the qualitative inspection. That's what's happening here. This plane, you can see the moisture in the trailing edge there is cold. Anyone have an idea how that moisture got cold? Compared to the rest of the structure that's warmer? It doesn't necessarily mean it's hot. I mean, this image has a max temperature of 8.8 degrees Celsius. So the red is 8.8 degrees Celsius. So it's still fairly cool. What? Any idea how we would make a plane really cold? What's the temperature at 40,000 feet? Negative 30, negative 40 degrees Celsius. So if you image a plane right after it lands, it's warming up, right? The water warms up slower than the structure does because it doesn't transfer the heat as well. Okay, so that water, it may even still be ice. It might freeze in there, and that's part of the reason we want to detect that. Is if you get moisture in a composite and it freezes, it expands. It actually starts to pop the layers of the composite apart. So it's fairly easy and quick to perform. Requires minimal equipment and just a camera, and that's what we're going to do in lab. Okay, you're going to do more of a qualitative. You can do general measurements about how big is it if you know pixel size, which we'll calculate in a minute. But so here, like I was saying, landing as the aircraft warms up because it's been cold soaked at altitude for sometimes 6, 8, 10 hours, right? If you're flying international. Move it indoors after sitting in the sun, it'll cool down. Opening doors of a temperature controlled hangar when it's warmer or colder. And any other, other scenarios that you may be able to come up with. So moving it into a heated hangar. So some common techniques that are active where we actually do it are shown here. So flash is just that. It's a flash. Anyone ever been to like a true portrait studio where they use the big flash systems? Have you felt the heat when they take a picture? That's enough heat. That quick flash of heat is enough to cause a certain amount of excitation. Now you have to have a very sensitive camera that takes a very quick picture of that, or even a video when that occurs. But you can use flash for that. Scanning there is a light, and we want to look at an object that's heating up or cooling down. So if we take a light that's on or a heat source that's on and we move it across an object, if my point that I want to scan is where my water bottle is here, if I move this light across, right, it's going to start to heat it up, and then it's going to cool off, right? So it creates a heating and a cooling as I scan past. So I point my camera at it, and I run that light back and forth. You can actually watch it change temperature, even if it's a very small temperature rise. When we get to cameras, we'll look at how sensitive they are. STEP is I've got some graphs of these too, but stepped is where you basically shine a light and you turn it up a little bit, turn it up a little bit, turn it up a little bit, you know, make it brighter, make it brighter, make it brighter, make it dimmer, make it dimmer, make it dimmer. And each time you're changing the brightness or the heat that the heat gun's putting out or something like that, you know, that's a temperature change that's going to cause a diffusion of energy within the part. And then the last one's modulating, and that's more of like a sine wave, like turning the brightness or the temperature of the heat source up and turning it down and turning it up and turning it down, right? Rather than stepping it up and down. It's a more smooth thing. And it can be heat or it can be cold. The one they're showing there on the right, C, that's a direct contact method. That can be things like a heat blanket or other stuff like that. We often use structures classes. Gail talked about or showed you what a hot bonder is. So you can use a hot bonder as a heat source as well for this kind of thing. Hot bonder are those rubberized mats with heating elements running through them. You can control them very, very precisely. So you can use those. So you can even use things like a hot water bottle, like you would have laid on when you had an ear infection when you were younger, or even heating up something like a brick or a block and then setting it on the part and then removing it, and then you take pictures. Obviously, you can't image it while it's sitting there, but then you remove it and image it once you remove that. So active heating is better for quantitative. We're going to use, we're primarily going to, well, we're going to use both. We've got an oven, that's an active heating technique. You're going to open and close hanger doors, that's passive. Fortunately, this always falls this time of year where the hangers and the outside aren't a lot different, but we make it work. But that's more, you know, then you're getting into quantitative for measuring things like thickness, depth, area, you know, adhesion, delamination, trying to take dimensional measurements. And so, you know, even though you're going to be doing you're going to be doing both active and passive heating techniques and cooling techniques, you're going to only be doing direct viewing or raw image viewing. You're not going to be doing any image processing. You're still going to be able to get some quantitative. And again, it's not going to be super duper accurate. It's going to be, or precise. It's going to be generalized size, about how big is the damage. Here's that graph, and I'll, you know, and this can be with visible light, you know, optical, showing those different kinds of heating, you know, the intensity over time of different heating techniques. So active heating with optical, it has the advantage of being non-contact. You know, some of these methods require contact. You can do various size areas, anything from small to large. You know, even, like I said, even a very small change in heat can be detected by these cameras. Oftentimes the alignment and positioning isn't critical, and then you can do these different patterns. And so the bigger graph of that is the pulsed is kind of on off. You can see an orange. Stepped is that gray. That's what I was talking about. You know, bring it up to a certain level, turn it up some more, turn it up some more. Modulated versus pulsed. You can see pulsed and modulated look similar. Pulsed in orange, a lighter orange yellow, I guess, and pulsed being the dark orange. You know, pulsed is, it's on and then off for a period of time. It's on for a very short, you know, that's kind of like a flash bulb. Whereas modulated is more of an on, you know, it's increasing, decreasing, increasing, decreasing without ever being off for really a period of time. And then scan, that's, you know, that's what I showed where I brought my hands in front of the water bottle is, you know, it kind of creates that rise and then that fall. Well, that's, you know, I'm at over here, I'm at the left side of the graph, and when I'm right here, I'm at that peak on the graph, and when I'm off to the right, then I'm at the tail end, the right side of the graph. We can also use things like forced air, heat guns, and whatnot. Trying to apply these evenly is a little bit tough with a heat gun, but it is doable. You can also use things like an oven. We'll use the oven in the NDT lab that we use for drying parts for LPI on the LPI bench. That actually works really well for parts that'll fit in there. You can put a part in there for 10 minutes, 15 minutes until it fully heats up to the 150 degrees or so that oven's at. And then when you take the part out, you can't actually image in the oven because it'll blank out your camera because there's so much residual heat in there. But then you take the part out of the oven, set it on a table or even on the floor, and start taking pictures of it as it cools back down to room temperature. And so, again, alignment and positioning isn't as critical, but things like heat guns, hair dryers, blowers, ovens, and then also cool air blowers if you're trying to do a temperature decrease, or even a refrigerator. You can put a part into the refrigerator, bring it back out and image it as it warms back up to room temperature. That's another option as well. So there's the pads on top for a heating blanket system or for a hot bonder. Right, those would be plugged on the top right there. They'd be plugged into the controller for a hot bonder, and they're those flexible rubber pads. Everyone's, ear infection, swab, what else? Cavity, tooth, pain, water bottle, right? Everyone's mom had one of those. Maybe not. I don't know. Mine had them growing up. We have one, I think, somewhere. But direct contact, like I said, hot or cold object placed in part. Now, the disadvantage is now you have to actually touch something to the part. Whereas before, with light or with hot air, you don't have to actually touch anything to the part. The cameras themselves never actually touch the part or the object being imaged. But it's a fairly slow process, not appropriate for rapid thermal interaction. So with like pulsed and lights and that kind of thing, you can have the camera and the light like taking pictures or flashing and taking pictures at the same time. They make some pretty cool. There's a company called Optigal and others that make very, very high speed cameras that work, infrared cameras that work with a flash system and can find, think about how little energy is actually being absorbed by a part when you just do a flash bulb towards it. But the cameras can pick up that real quick increase and decrease in energy. And they tend to be used to find like real fine and doing measurements. They can do a really good job of measuring size and that kind of thing, because then the image is processed as part of them. They usually have a computer that processes the image, controls everything, so they're pretty neat. But for these, again, they tend to be more of a qualitative system, and it's, you can't actually take a picture while the hot bonder or the water bottle or whatever else is sitting against there. So you have to do it as it cools off or heats up afterwards. Nice part is, like, especially with a hot bonder, you have very, very precise control of the temperature, right? How long it's heating, how hot it's getting, how it's ramping up or ramping down. Some of the others, electromagnetic, induction heating, and or microwave heating. We can use those to heat it, right? You use a microwave probably a lot. You're a college student. But also induction heating, which is, the same thing that happens when we put parts in the mag particle bench and they warm up. You put a part in a magnetic field, or you run electric current through a part, and the magnetic field it generates heats the part up. And those can heat up. Here we're just getting parts warm to the touch, but I worked in a forging plant before I came here. We used induction furnaces to heat the steel. Our steel we didn't have like a gas furnace. It went through electric coils. And normally it would get the steel to about 12 to 1400 degrees before it was forged. If something went wrong, it would get the steel to 1700 degrees and melt it. And then you would have to pull the coils, and it was a whole line would be shut down for hours. So, induction heating is used to get stuff really, really hot. So you can use that for this kind of thing. Microwave heating you can't use with metallic parts, though. Some of you have probably put metal in your microwave. If you haven't, it's kind of cool to watch. It's not good for your microwave or whatever metal objects you put in there. Back in the day, we used to put a CD in there. Anyone ever done that? You guys probably don't have CD. It creates like a lightning pattern in the metal foil that's inside the CD. They're kind of but the neat part like that, microwaves, where do they heat the food when you put them in there? The water molecules, where does it kind of heat from? Heats from the center out. And so you can actually use microwave to see the diffusion of energy from the center of a part to the outside. So it's kind of a unique way of being able to image. That's what I got there. It can be used to heat the interior to observe diffusion of energy from the inside and then out. Continuous scanning, used when the inspection area is larger than the field of view. You can imagine something like this: as you have a heat lamp or a heat gun, and you have your camera. And if you have the side of an airplane, you go down the side of the airplane with, especially doing like a video camera, and you just kind of go along right like this. And you can scan like the side of a large area that way. So alternate of start-stop that you get with discrete areas. So they're moved in tandem relative to each other. Again, they do make like these scanning devices that are designed to scan an area too, if you don't want to do it manually. Can also be pulsed or modulated, other stuff like that. So then after we've heated our part, then we have to detect it. And originally, kind of the earliest forms of thermography or thermal inspection had used spot detectors. And so how many of you use one of those? They're like a little heat of like an infrared thermometer. It's like a little gun thing. You pull the trigger, point it at something, shoots a laser, and you get temperature at the spot. Okay, now imagine that with 5,000 or 10,000 of those all together. That's essentially what a thermal camera is. Okay, it's like having those little spot detectors, heat spot detectors. It's having thousands of them, and they create a picture or a grid of temperatures. So early spot detection allowed remote measurement of IR and only test one point at a time. For us, they're not as useful as an analysis tool. They're good for finding like a bearing that might be failing, or if you've got a dead cylinder on an engine, a dead cylinder would be colder than the rest. You could shoot each cylinder one at a time. But for ours, we're going to use an infrared camera. And these were first introduced in the 1960s and allow the remote measurement of infrared energy. So again, they're basically like thousands of spot detectors all laid out in a big grid or grid. And the amplitude of each pixel gives you a temperature. It's correlated to the surface temperature in that area. And so for thermography, you can use it. If you calibrate the camera, you can find absolute temperature. What is the temperature of this object at this point? However, what we're more interested in when we're trying to see how's energy diffusing and what's going on in a part, what we're most interested in seeing is how does this spot compare to the spot next to it, compared to the spot next to that, compared to the spot next to that, and the spot below it and below that, and to an, we're comparing pixel to pixel or point to point on an object. So we do have to calibrate our camera. We do have to go through and we have to calibrate it for the material surface. So we get a fairly accurate temperature, but at the same time, we're not really concerned with, are we getting the perfect, like, is this the exact temperature of the object? It's, how do these temperatures compare across the surface? And so there's some points that go along with this. So infrared cameras have performance parameters that you have to be aware of when you're either selecting your camera or that will provide the limitations for using a certain camera. So the first one is thermal sensitivity, and this is what kind of a temperature difference can you detect between each pixel. We have two types of cameras you're going to be using in lab. Our FLIR E95 is a handheld higher resolution camera. That's, again, that one retails for about, they don't make it anymore, but at the time they've upgraded it, but they retail somewhere in the $8,000 to $10,000 range. For $8,000 to $10,000, you can detect differences from pixel to pixel of approximately 0.03 or less than 0.03 degrees Celsius. So that is an extremely small temperature difference, especially for what we're going to be doing, right? 0.03 degrees Celsius. Our FLIR One Pros, which is about a $400 camera that plugs into an iPhone or an iPad, or we've got a couple that plug into Android devices, those have a thermal sensitivity of 0.07 degrees Celsius. Still pretty good though, right? Less than a tenth of a degree. Accuracy is what's the error, and this is what I was talking about. We're not as concerned with the being as accurate as possible. We're more concerned with the difference from pixel to pixel. So that's where that sensitivity comes in. You can see the accuracy really isn't nearly as close as the sensitivity, right? The FLIR E95 plus or minus 2 degrees Celsius. The FLIR One Pro plus or minus 3 degrees Celsius. Okay. So if the temperature in the room is 70 degrees, the FLIR E95 might show a pixel anywhere from 68 to 72, but it's going to show all of them in that range. But from one pixel to another, the difference is only going to be about 0.03 degrees. Okay, so even though the accuracy is overall, it's not pixel to pixel. Okay, keep that in mind. If one pixel is reading 2 degrees high, the entire sensor is reading probably 2 degrees high. And so they're still going to have that sensitivity difference of 0.03 degrees. The third part there is thermal range, and that's the range of temperatures that the sensor, the IR sensor, is able to detect, right? Because temperatures ultimately are different amounts of energy, right? And then not to mention then heat, infrared is a range, so there's different frequencies of heat, but we just look at them all as kind of combined together for the temperature of an object. But the E95, it has three ranges you can set your camera in. So you can set the sensor to look at -20 to 120 degrees Celsius. And remember, water, this is water boils at 0 or freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So this is our normal ranges that we're going to experience in everyday life. It has a range from 0 degrees Celsius to 650 degrees Celsius. And then it has a range that goes from 300 degrees Celsius to 1500 degrees Celsius. So for most of the imaging we're going to do, you're going to probably be in one of those first two ranges, right? And most of the time, we're probably going to be in that first range, -20 degrees Celsius to 120, right? That is a 140 degrees Celsius range. It's a narrower band, so it's going to be more, it's going to provide better accuracy within that band than the others. And it covers most of the temperature we'll do. It's rare you'll heat a part up. You really don't have to heat a part up that hot. The oven, probably the part you're going to heat the most will be the one that goes in the oven. That's 150 degrees Fahrenheit, which is, anyone good at doing conversions? Is that about 75 degrees Celsius? It's less than 100 degrees Celsius because boiling is 210 degrees Fahrenheit. So, even our oven, the parts we heat in the oven, you can image in that first range right there. Now, if you had, say, an engine that you were going to image, you were going to run the image and run an engine and want to take images of it, you might have to bump it up to that 0 degrees Celsius to 650 degrees Celsius range. Or if you were going to do something like a turbine engine, you're going to try to image the exhaust on a turbine engine, then you might have to go to that 300 to 1500 degrees Celsius range. But for the most part, you're going to use the -20 to 120 Celsius. The Flare 1 Pro only operates in a single range. You can't select it. It's -20 degrees Celsius to 400 degrees. So you can see it's a wider band. It starts at the same starting point, but it doesn't go up into those real high temperature ranges that you get with the higher end cameras. Other things when we're measuring, we need to know our array size. And this is similar to if you think of image resolution from like a digital camera. The camera is built into your smartphone. So this is the number of pixels that the sensor is able to detect. Okay, it's the number of simultaneous temperatures it takes when you take a thermal picture, a thermal image. Don't confuse it with the display screen. Your display is going to have a different resolution oftentimes. So on the E95 camera, for instance, the display is lower resolution than the actual images. Okay? If you pull an image onto your computer and blow it up, you'll be able to see it full size, more of a full size thing. So, but we are concerned with the image resolution. We can display it on whatever we want. We can print it whatever size we want. If you print it really big, it's going to pixelate. You've probably experienced that before, where you have a low resolution image. But the FLIR E95, you can see width is 464 pixels. The height is 348 pixels, so it's not even what would be considered standard definition if you're used to like standard definition, high definition, ultra high definition. Standard definition is 640 by 480, if I remember right. So you can see these are not, they don't have the resolution that a visible light camera does. And that's because you can get cameras that are high def thermal cameras. You're going to be spending upwards of $80,000 for one of those. They're very, very expensive. It's very expensive to make the sensors that have that kind of resolution. But for our purposes, the 464 by 348, that gives you 161,000 pictures. It's a 4:3 ratio, which is similar to what an old school television had. The more square looking picture. Still a rectangle, but it's not like a high def, like what your laptops and tablets have, which are wider, are more of a 16:9 resolution. The FLIR One Pro, 160 by 120, so you can see that is, it has a lower resolution number of pixels by roughly an order of magnitude of 10, 19,000 instead of 161,000. What it means, you can still do imaging the same, you just may have to get closer. We'll look at figure out how far you have to be for a given size, given resolution and a given expected flaw size. The field of view is determined by the camera lens. We're familiar with field of view, hopefully from borescopes. That's the angle of view. And so the FLIR One Pro has a 24 degree by 18 degrees. So it's going to spread those 464 pixels across 24 degrees wide. It's going to spread those 348 pixels across 18 degrees tall. And if you do the math, 24 divided by 18 gives you the same 4:3 ratio. So its pixels are square. You compare that to the FLIR One Pro, it's a wider angle, so it takes that 160 pixels, it splits it over 55 degrees, 120 pixels over 43 degrees. It's not exactly a 4:3. So you get more of your pixels are rectangular rather than square. Okay? You can also see the pixels are spread over a wider angle of view. It's a wider angle of view, less pixels, so you have to be significantly closer to get the same pixel coverage of a given area. Okay? So given the array size and the field of view, you can calculate the pixel area. How big of an area does each pixel cover at a given distance? And for a flaw, we want to have a minimum overlap of 9 pixels. So to say, yes, this is a flaw, or no, it's not a flaw, you have to have a minimum of 9 pixels, or basically a 3:3 square. Okay? And so 9 square pixels for a discontinuity. So lower resolution cameras, you have to be closer. Narrow field of view, so a narrower field of view, right, the smaller angle, that's going to put more pixels in a given area. Wider field of view is going to spread those pixels over a wider area. And so you result in a smaller scan area, but greater detail with that narrow field of view. And so again, like our FLIR E95, you can actually change, there's different lenses you can get for it. They make a wide angle lens, a narrow angle. We have the medium, what they call their medium angle lens. The FLIR One Pro is like your phone camera. It's a fixed lens. You can't change the lenses out, or you can't change the field of view on it. It's kind of the difference between a professional, SLR type camera and a point and shoot or a phone camera. Right? One's more fixed, one's not. So how do we know? What it comes down to is we have to know how far away we can be to find a flaw of the size that we expect to find, or that we have to be able to find. And that's known as your working distance. So here's what we have. What is the smallest discontinuity you can find at 10 feet? And I'm using the FLIR E95 for this example. So if we have, and we're just looking at the horizontal right now. And remember, these are square pixels, so it'll work for both directions. If you're dealing with the E90 or the FLIR One Pro, which has rectangular pixels, you have to go with the smaller direction. But if we have a resolution of 464 by 348, our lens is 24 degrees. If we look at this scenario from above, looking at the horizontal aspect of a picture, what is the smallest discontinuity we can find? And remember, it has to be 3:3, so we got to have at least 3 pixels covering it horizontally, 3 pixels vertically. So what is the smallest discontinuity you can find? What is the length of 3 pixels wide? Pull out pens and paper, see if you can figure it out. It's a little review from trigonometry class here. Anyone have an idea for how we start? SOHCAHTOA. Okay, so trigonometry is important. So let's look at just half of our triangle, okay? Because we have to have that right triangle in order to do trigonometry. So 232 pixels, we're 10 feet away. First thing we got to kind of figure out, how wide is this 232 pixels? How do we find that? What is it? What do we know? So we know an angle, right? Angle of 12 degrees. We also half the angle, right? It was a 24-degree angle. We're looking at half of it. So we know the opposite and we know the adjacent. So what is opposite over adjacent? What do you use for that? TOA. Tangent is opposite over adjacent, right? Okay. So we have tangent of the angle, 12 degrees, equals opposite, we're trying to find the x, over adjacent. Right? So how do you solve that? What's tan of 12 degrees? A number. Let me pull up my what's that? How about 0.176? Anyone else get that? What's that? What'd you get? 0.212? Tangent of 12? Uh-oh. Is mine in radians? What happened here? Sorry, tangent of 2, 0.213. I think I put 10 in, okay? So tangent of 12 equals roughly it's 0.21255656167, yeah, okay? Equals x over 10, so then we have to multiply both sides times 10, right? So that side is equal to 2.13 feet. Now what do we have to do? We have to figure out the length of 3 pixels. How do we figure out the length of 3 pixels? How do we figure out the length of 1 pixel? Okay, so to figure out the length of 1 pixel, well, L of a pixel equals 2.13, and remember this is feet, divided by the number of pixels, 232. Oops, divided by 232. Yep, 0.0092 feet, which also equals, yep, times what to get inches? Because it'll be easier to work in inches. Right? Times 12 gives us 0.11 inches. Okay, now that's 1 pixel, but we have to have an overlap of 3 pixels, right? What's that? So we multiply that times 3. We go to the next slide. So approximately 0.33 inches, so a third of an inch. Okay, so at 10 feet, we could in theory find a flaw down to about 0.33 inches, or a third of an inch. Okay, so pretty sensitive at a camera. So we can get a pretty big area. Plus, we're going to be imaging an area. This is only half, so we'll be imaging an area that's about 4¼ feet, which is 4 feet 3 inches. So we'll be imaging an area like this, right? At 10 feet. Okay. If our expected flaw, if our allowable flaw is smaller than 0.33 inches, what would we have to do? If we have to find a flaw that's smaller than that, what would we have to do? We'd have to move closer. What if we could have a flaw up to 1 inch? What could we do? We could potentially move away and image a larger area at one time to make it go faster. Okay? So that's where we will leave off. And